Hello student, good morning. I am Dr. Kumar Sinha, Professor of Chemistry. Today I am going to discuss formation of complex compound. Last class I have discussed formation of colored ions. Now I am going to discuss formation of complex compounds under D and F block elements. Complex compounds are those in which the metal ions bind a number of anion or neutral molecules, giving complex species with characteristic properties. A few examples are FeCN6 3-. It is a complex ion having 3 negative charge, 3-. FeCN6 power 3-. Means a complex compound is written in a big bracket. FeCN6, it is written in a big bracket and power is now here 3-. This is the anion. Other example is FeCN6 power 4-. Next example is CuNH3 whole 4 power 2+. Means it is a cation. And PtCl4 2-. This is anion. The chemistry of complex compound is this discussed in transition metals. Okay, the transition metals form a large number of complex compounds. This is due to the comparatively smaller size of the metal ions. Here important point I am repeating, the transition metals form a large number of complex compounds. This is due to the comparatively smaller size of the metal ions. Here transition metal ions are smaller in size. And other reason is their high ionic charges. They have more charge. Then this is the second point, high ionic charges. And third point, availability of d orbitals for bond formation. Then cause for complex formation I have told you. There are three regions to form the complex ion. First, comparatively a smaller size in the metal ions. Second, their high ionic charges. And third, availability of d orbitals for bond formation. Because ligands, as for example H2O, cyanide, NH3, chloride, bromide, iodide, these are actually ligands. They can make bond with vacant d orbitals. They can donate electron to the vacant d orbitals and can form complex ions. Now I am going to discuss catalytic properties. Catalytic properties. The transition metals and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states. Again you listen, this activity is due to their ability to adopt multiple oxidation state and to form complexes. Vanadium fifth oxide. Vanadium fifth oxide in case of contact process. Finely divided iron in Haber process and nickel in catalytic hydrogenation are some of the examples of transition metals which acts as a catalyst. Catalyst at a solid surface involve the formation of bonds between reactant molecules and atoms of surface of the catalyst. Here you should understand action, how they are making bond. Okay, catalyst, what is the role of catalyst here in any reaction? Okay, where catalyst is used, what catalysts are doing, that I am telling you. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atom of the surface of the catalyst. Particularly first row transition metals utilize 3d and 4s electrons for bonding. Catalyst, that is transition metals, particularly in first row transition metals, utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of reactants at the catalyst surface and also weakening of the bonds in the reacting molecules. Means when reactant will come in contact with the surface of catalyst, then these reactants will make bond with catalyst on catalyst surface. Okay, more and more, because they are making bond, and so more and more reactant will come near the surface of catalyst and they will make the bond. Okay, that's why concentration will be more and more on the surface of catalyst. And also what it will do, that catalyst will make bond with the reactant molecules, first things. And second things, they will weaken, means catalyst will weaken the bond among reactant molecules. Means one side they are making the bond between catalyst molecules and reactant molecules, and other side among the bond among the reactants, that will break, that will become weak. Okay, then these works will go on the surface of catalyst when reactant will come to the surface of catalyst. And also you can understand that when they will make the bond, catalyst will make the bond with reactants, the activation energy is lowered, activation energy decreases. That's why reaction takes place quickly. Also, because the transition metal ions can change their oxidation state. Obviously, that transition metal ions can change their oxidation state. They become more effective as catalyst. When they will make a change in their oxidation states, they become more effective as catalyst. For example, iron third. Actually, 3 example already I told you that vanadium oxide in contact process, when you are making sulfuric acid, that time it is made by contact process. Then vanadium fifth oxide, means vanadium oxide function as a catalyst. Second, I told you Haber process, means formation of ammonia, manufacture of ammonia. That time finely divided iron is used as catalyst, and nickel is also used as a catalyst in hydrogenation. Okay, these examples I have told you. Now, further example, iron third. Iron third catalyzes the reaction between iodide and persulfate ions. Okay, iron third catalyzes the reaction between iodide and persulfate ions. 2I minus means iodide ion plus S2O8 2 minus, it gives 2 product, I2 plus 2SO4 2 minus, means S2O8 will give, or it will convert to sulfate. Okay, here iron third when function as a catalyst, then what will happen, that iodide means potassium iodide, like here 2I minus, and persulfate means S2O8. Okay, then this iron third means catalyst catalyzes the reaction between iodide and persulfate. There iron is used as catalyst. Now other example, that catalytic action can be given as 2Fe3 plus, Fe3 plus, 2Fe3 plus 2I minus. It will give 2Fe2 plus I2. Okay, 2Fe3 plus 2I, it gives 2Fe2 plus iodine I2. Then this is also this happens due to the catalytic action, this reaction. In this reaction catalyst is used. Now another example I am telling you, this was a ferric 2Fe3 plus, now I am telling 2Fe2 plus ferrous plus S2O8 2 minus means persulfate, ferrous plus persulfate. In this reaction also catalyst is used, and in this reaction ferrous will convert to ferric and persulfate will convert to sulfate. Okay, persulfate ion will convert to sulfate ion. Now I am going to discuss formation of interstitial compound. Formation of interstitial compounds. Question is asked. What is actually interstitial compound? Now I am going to discuss. Interstitial compound are those which are formed when small atoms like H, C or N means hydrogen, carbon or nitrogen. So these are small atoms are trapped inside the crystal lattice of metals. Interstitial compounds are those which are formed when small atoms like H, C or N are trapped inside the crystal lattice of metals. Okay, in the crystal lattice of metals, when hydrogen, carbon, nitrogen, which are small atoms, are trapped, then That compound is called interstitial compound. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, interstitial compounds example, first example, TIC, titanium carbide, TIC. Second, nitride, Mn4N. Third is, again it is hydride, Fe3H. Okay. And next example is VH, vanadium hydride. But hydrogen is not 1 unit, it is less, 0.56. VH, H is not complete 1, it is less, around 50% only. That is a VH 0.56, means 0.56, half you can tell. And titanium hydride, here it is not complete 2, it is 1.7, TiH 1.7, etc. These are the example of interstitial compounds. I am telling TIC, titanium carbide, okay, Mn4N, third is Fe3H, 4 is VH, but H is 0.56, and titanium hydride, but hydride is H is 1.7. Okay, the formula quoted do not of course correspond to any normal oxidation state of the metal. These are not you can say correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compound. Okay, because of the nature of their composition is little different. These compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are, first I am telling you, physical and chemical characteristics. Physical and chemical characteristics of these compounds are as follows. First, they have high melting point, higher than those of pure metals. Okay, because you are talking about interstitial compound, this is different from pure metals. Okay, because some this H, C and N are trapped, that's why it is not pure metal, it become impure. Then first characteristic is they have high melting points, higher than those of pure metals. Second, they are very hard. Some borides, boron, related to boron, some borides approach diamond in hardness. You can understand, diamond is the hardest substance in the world till date. Actually, parallel to diamond, some other can say compounds are there, but till date they have not got a status of highest. Can say highest distance hardness. Till date, diamond is the only hardest you can tell. Then now boride is also approach diamond in hardness, means so much hard. Interstitial compounds are particularly borides are similar to diamond in hardness. Next properties, they retain metallic conductivity. They retain metallic conductivity means they can conduct electricity. And one more properties is their characteristics, they are chemically inert. Okay, interstitial compounds are chemically inert. Now I am going to tell about the alloy formation. Alloy formation. What is the alloy? Already you know, but again I will tell you. An alloy is a blend of metals. An alloy is a blend of metals prepared by mixing the components. Okay. An alloy is a blend, means mixture. An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous. Alloys may be homogeneous solid solution in which the atoms of one metal are distributed randomly among the atoms of other. Okay. Such alloy are formed by atoms with metallic radii that are within about 15% of each other. Means radii should be almost similar. Okay. Because of similar radii, 15% to each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are alloy, example of alloy, that is the ferrous alloy. Now this first example I am telling: chromium, vanadium, tungsten, molybdenum and manganese are used for the production of variety of steel and stainless steel. Different type of steel and stainless steel depends upon these alloy because iron is the main, but sometimes chromium may be mixed, sometimes in ferrous vanadium may be mixed, sometimes tungsten may be mixed, tungsten is W, sometimes molybdenum may be mixed, sometimes manganese are used. Then they will form various type of ferrous alloys. These are called ferrous alloy because ferrous is common, but with ferrous chromium may be mixed. Correct? With ferrous vanadium may be mixed. With ferrous tungsten may be mixed. With ferrous molybdenum may be mixed. With ferrous manganese may be mixed. I mean, different alloys they are forming. That's why they are called ferrous alloy. Alloys of transition metals with non-transition metal. Now we see alloys of transition metals with non-transition metals such as brass. Example is brass. Then copper and zinc. Then you know zinc is non-transition. It is in a group of Zn and in a group of transition metals, first series. But zinc is not the transition metal, but it is making copper and zinc. That is called, this alloy is called brass. Other example, transition and non-transition. Here zinc is non-transition and copper is transition. And in bronze, copper and tin. Then copper is transition metal, tin is non-transition. Okay, then these are, I can say, I told you alloys of transition metals with non-transition metals. And these are also have considerable industrial importance. Then I told alloy formation. Now one question I want to discuss: what is meant by disproportionation of an oxidation state? Give an example. This is the question. Okay, the important question is this is asked also in examination. Then explanation I am telling you what is the disproportionation of an oxidation state. When a particular oxidation state becomes less stable, listen here carefully, when a particular oxidation state becomes less stable relative to the other oxidation state, one lower, one higher. Okay, suppose now any oxidation states becomes less stable relative to the other oxidation states, one lower, one higher. It is said to undergo disproportionation. For example, manganese 6 becomes unstable relative to manganese 7 and manganese 4th in acidic solution. Suppose you have taken manganese 6. Now manganese 6 in a acidic medium becomes unstable and it will form two products, Mn7 and Mn4th. Manganese 6, that is the MnO4, in this MnO4 2 minus, in that manganese is 6 oxidation state, but in acidic medium means in presence of acid it will give two, total 3 product, but 2 will be of Mn, one will be MnO4 1 minus, it was 2 minus, now it became MnO4 1 minus, and other product is MnO2, means Mn is 4, then it is giving two product Mn7 and Mn4. Mn6 has given two product of Mn only, Mn7 and Mn4th. Then this is actually called disproportionation. When you are getting product of the same metal, but oxidation state is different. Oxidation state is different, then it is called disproportionation. Then reaction I told you 3MnO4. Here Mn is 6 oxidation state. 3MnO4 2 minus plus 4H plus, it gives 2MnO4 1 minus. Here oxidation state is oxidation state of Mn is 7 plus other product is MnO2. Mn is 4th. Then now you are getting two product of the same metal. Oxidation state is different, 7 and 4. Okay, plus 2H2O. Then here two product you are getting of Mn only, 6 converted to Mn6, manganese 6. Now it is giving manganese 7 and manganese 4th. Okay, and this is called disproportionation. Then balanced equation I am telling you, 3MnO4 plus 4H. Here MnO4 I told you 6 state plus 4H, it is giving 2MnO4 1 minus plus MnO2 plus 2H2O. This I have explained what is the disproportionation. Example also I have given. Now I am going to discuss oxides and oxyanions of metals, means transition metals. Oxides, you know that transition metals forms many oxides. Not only oxide, they form oxyanions also. Okay, then now I am going to discuss oxides and oxyanion of metals. This only important compounds of transition elements. I will tell you some important compounds of transition elements in the form of oxides and oxoanions. Okay, oxoanions of metals. These oxides are generally formed by the reaction of transition metals with oxygen at high temperatures. All the metals except scandium form metal oxide, metal oxides, which are ionic. Okay, Mo is ionic, M is metal. Then all the metal except scandium, this is a exception, and question is important. Only this type of question in examination they will ask. All the metal except scandium form metal oxide, Mo, which are ionic. The highest oxidation number in the oxides coincide with the group number and is attained in scandium O3, Sc2O3, highest oxidation number in the oxides coincides with the group number. What is the group number? That is the oxidation number, and is attained in Sc2O3. In scandium, oxidation state of is +6. Okay, not +3. Scandium +3, Sc2O3. Okay, +3. Then here I told you that coincide with group number and is attained in scandium O3 to Mn2O7. Then in scandium is +3 and Mn2O7 means Mn has +7 oxidation state. It varies according to the coincide with the group number. Then it start with scandium and it will go with manganese, maximum +7. Actually Sc2O3, then O3 is telling about scandium and Sc2 is telling about oxygen oxidation number. Just reverse way, trans way. Sc2O3, then Sc2 is the oxidation number of oxygen, and Sc2O3 and 3 is the oxidation number of scandium. And in Mn2O7, 7 is telling for manganese, Mn, and 2 is telling for oxygen, Mn2O7 cross. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Correct? This is the 7 is the highest. Beyond group 7, no higher oxides of iron above Fe2O3 means Fe3 plus is known. Only Fe2O3 is known. Okay. Besides the oxides, the oxocations stabilizes vanadium as vanadium fifth as VO2 1 plus. Okay. Beside the oxides, the oxocations also oxocations stabilizes vanadium V5 as VO2 1 plus. Now it is stable. VO2 1 plus is stable, and also it stabilizes, oxocation stabilizes V4 as VO2 plus, vanadium oxide. Okay, V4 will be oxidized as stabilized as VO2 plus, vanadium oxide, and titanium 4th will also means oxocation will stabilize titanium 4th as titanium oxide, TiO2 plus. As the oxidation number of a metal increases, ionic character decreases. Remember it. Question is asked. As the oxidation number of metal, means transition metal, increases, ionic character decreases. As the oxidation number of metal increases, ionic character decreases. In the case of Mn2O7 is a covalent. Mn2O7 is a covalent green vial. Question is asked. Mn2O7, here oxidation state of Mn is +7. Mn2O7. This is a covalent character. Mn2O7 is a Mn2O7 has covalent character. It is called covalent green vial. Its color is green and it is a vial. Even CrO3, chromium trioxide, CrO3 and V2O5, vanadium pentoxides have low melting points. Correct? There's because of higher oxidation state V2O5, then vanadium is +5. They have low melting points. CrO3, Cr has +3 oxidation state. Then CrO3, chromium oxide, vanadium oxides have low melting points. In these higher oxides, the acidic character is predominant. This question is again asked. Means this in CrO3, V2O5, actually here they have these two compound are acidic. Okay, in these higher oxides the acidic character is predominant. Question is asked. V2O5 and CrO3. Now further I want to tell you this I told about the Mn2O7. Mn2O7 gives, because this Mn2O7, the covalent nature I told you, and it is called green vial, Mn2O7. Thus Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. Mn2O7 gives acid HMnO4, manganese acid HMnO4, and CrO3 gives H2CrO4, chromic acid, H2CrO4 and H2Cr2O7, both are acid, H2CrO4. Okay, monochromate or dichromate, but it is a acid form, chromous acid. Okay, H2CrO4 and this chromium H2C, potassium dichromate, what we are telling, but here potassium is replaced by H2. It is chromic acid, H2Cr2O7. And also can say V2O5, more about the V2O5. V2O5 is a amphoteric. Question is asked. 2-3 question I told you. What I am telling you important, or question is asked means question is already asked and may be asked. Okay. Then V2O5, remember, vanadium pentoxide is amphoteric. Amphoteric means it can behave as acid as well as base, though mainly acidic. Okay, V2O5 is amphoteric, though mainly acidic, and gives VO4 3 minus as well as BO2 1 plus salts. This because it is amphoteric, it is giving acid. Generally it will give acid, and also it can form salts. BO2 plus 1 plus means what? It is giving cation. It is giving cation. Okay. And BO4 is 3 minus, that is anion, means because it is amphoteric, hence it can give cation as well as anion. Then example of cation is BO2 plus, and anion BO4 3 minus. Okay, and this I told you about the these things, Mn2O7 and about the CrO3. Also I discuss about B2O5. In vanadium, there is a gradual change from the basic B2O3 is basic, to less basic B2O4 and to amphoteric B2O5. Correct? Here sequence and try to understand. In vanadium, there is a gradual change from the basic B2O3 to less basic B2O4 and to amphoteric B2O5. B2O5 is amphoteric. Correct? Then slowly it decreases. It changes from basic B2O3 to less basic B2O4 and to amphoteric B2O5. B2O4 dissolves in acids to give BO2 plus. B2O4 tetra, divanadium tetraoxide, B2O4 dissolves in acid to give BO2 plus salts. Similarly, B2O5 reacts with, because it is amphoteric. Similarly, B2O5 reacts with alkalis as well as acids to give BO4 3 minus and BO4 1 plus. Correct? Because it is amphoteric, it can give acid and base both. B2O5 reacts with alkalis also because it is amphoteric. B2O5 reacts with alkalis as well as acids to give BO4 3 minus, means anion, and BO4 1 plus, that is cation, respectively. The well characterized CRO, I am talking about chromium monoxide, CRO. The well characterized CRO is basic. Question is asked. CRO is basic, but CRO3 is amphoteric. Remember it, both questions are important. Both points are important. CRO is basic, but CR2O3 is amphoteric. Okay. Then this I have discussed about these things, oxides and oxoanion of metals. Now next class I will discuss, you can say, compounds of transition elements, important compounds of transition elements. As for example, potassium dichromate. Potassium dichromate is very, very important. All reactions are very, very important. Then potassium dichromate and potassium permanganate. Okay, next class I will discuss. Thank you.